Hello everyone. In this chapter, we want to learn about the single factor experiments. So in the previous chapter, we talked about the general concept behind the design of experiments. It's like that. What are we designing when we say design of experiments? In fact, it's so we define our factors, and then we design. When we say design of experiment, it's like that. But which factors we are gonna change? So we choose those factors to change. And then we said that, okay, so we have three different strategies. Then we are talking about the methodology for the experimentation. And so in this chapter, we are going to work on one of them, which is the single factor experiment. So the single factor experiment, it's basically, we are going to change one of the factors. And when I say factor, it's like that. We're talking about the factors that they are that they would affect our output, like our result. So that would be factors. Like, for example, when we're talking about regression model, the independent variables like X that we had, those were our factors. Those could be our factors. And like always, the materials that you see here, the notes, they are copyrighted material from Professor Alex Benledis. So we're in chapter 4. Our objective in this chapter is that we want to discuss a little about the randomization, replication, and blocking. But the blocking, we're gonna have one whole chapter for the blocking later. We want to talk about experimental design analysis for comparative studies, and also talk about different tools that we can use, like, for example, ANOVA table, T, and F tests that we had so far. So it's like that we are going to expand the T test and like F test. Make sure that you can read the T table and F table before going any further. Okay, so we had it before. So when we talk about the independent variables or factor, we would say that it's like X that we had in the regression models. And when we are talking about the dependent variables, they are like Y. So the output of our system, we would say that as the dependent variable. So single factor experiment, this is an experiment which studies the effect of a single independent variable or factor. It's like that, for example, in the previous chapter, I talked about the playing golf example. So we said that, okay, we want to know that what's the different factors that they're going to affect my, like they're going to influence the score that I would get in golf, playing golf. And we said that, for example, let's say if the weather is cold or warm, or if I play in the morning or afternoon, if I drink water or something else while I'm playing. So all of those ones, these are that I said is like factor. When we say single factor, it's like that I'm going to focus on one of them and consider the rest of them constant. The level at which the factor is studied are often called treatments. In an experiment, there will be 2 or more treatments. The factor can be quantitative or like qualitative. So when we say that like quantitative, like temperature, 50, 60, 70, that's the, like, because we can say that is 50, 60, or 70, like let's say these are levels, 50, 60, 70. But the factor of like temperature, it could be our quantitative. And when we are talking about the qualitative, it's like that we would say like wood species, A, B, C, D, or other examples that we could have for the qualitative. Like drinking water or not, or something else, that's the qualitative. So drinking water as a fact, like drinking as a factor is going to be qualitative in the golf example that we had. So this experiment determines if there are significant difference in the result of the measured response variable, depending on the level of the independent variable, like this would have. Here are just some example of single factor experiment. For example, the analytical labs analytical labs like method comparisons, product development. Like in the product development, we would say comparing new product to the competition. So you are just comparing the like two products. So this is going to be just one single factor, right? In process optimization, comparing different operating conditions that we would have. Quality control, comparing like that would compare the different suppliers' raw material. Okay, so here it's good that you would go to the and look at the tutorial, which is like a practice problem for us, right? And in the tutorial, example 1, is the study really a design experiment or not? So you want to say that if it's the design experiment, we could call it a design experiment or not. So here we want to talk about the consideration in designing a single factor study. So we won't guarantee the validity of the experiment with randomization. We said that in the previous chapter as well. We said that randomization, replication, and blocking are 3 important keys that we need to consider when we are talking about design of experiment. So replication, obtain a measure for reproducibility. It's talking about the error magnitude. And blocking, we would control sources of variability by blocking. So we always say that block what you can and randomize what you cannot. Regarding the randomization, it's very important to have it to prevent personal bias on the part of the experimenter or others from entering. To eliminate biases in estimated effect caused by trends, the error or other independent variable, to prevent time order effects from masking the results, to ensure that the observed effects were caused by the change to the factor made by the experimenter. So it's not just like, for example, it's not because of lurking variables or something like that. To make certain that the significant tests are based on valid random variable. So always you want to randomize, and randomize. If randomization is not possible for some reason in your experiment, at least be aware of that, like the possible problems that it's gonna make. Okay. The honors of this experiment essentially consists of comparing the variability between treatment levels with the background. So with background variability, which you would say within treatments. So it's like when you say between treatments, it's like that. I have treatment number 1, 2. So in an example, I'm going to show you quickly. 1, 2, 3. So what's going to happen between them? Like we would say between apple and pear, right? But within treatments, it's like that. What's happening inside them? Like we would say within short period of time. So the latter, we say that it is experimental error, like the within treatment, often referred to as inherent, like underlying intrinsic error, or residual, that we were saying. I've heard about that. So obtaining a reliable estimate of the experimental error is key to the analysis, as we talked about that before. To obtain an estimate of experimental error, you must replicate your experiment. And when we say replicate, is, as I said, it's like from 0 to 10, like it's like the whole stage. You have to replicate the whole process, like the whole experiment. Here is, we can say what sources contribute to experimental error in an experiment, like measurement error, uncontrollable or unknown errors, and assigned source of error. Okay, so here is a question. Suppose I want to compare 4 manufacturing processes for the same product. How many replicates should I take for my study? And as I said, replicate means that conduct the entire experiment from start to finish, like from scratch. So I asked you this question, what would you say? So how can we decide how many replicates we can? I have like, let's say 4 manufacturing processes, and I want to know that how many replicates do I need. So you can pause the video or think about it a little, and let's then come back and watch the rest of it. So the answer is it depends. Depends on the situation that they're working with. We need to know that what difference you want to detect, a standard deviation of process, like the response, and what degree of confidence is desired. Then we can say that, okay, so how many replication we want to have. Also, regarding randomization, so randomization and replication, they are very attached. So you can see that I go back and forth with them. So we would say randomization has many benefits, as we discussed earlier. In addition to those ones, randomization helps us not to have bias, not to be biased in our experiment. So in addition, randomization eliminates the requirements needs for the normality assumptions.